The 2025 Nobel Prize in Physics went to John Clark, Michael Debye, and John Martinez for proving that the strange rules of quantum mechanics don't just apply to tiny particles, they apply to objects we can actually measure. At the heart of their work is quantum tunneling. In the everyday world, if you throw a ball at a wall, it bounces back. But shrink that down to the subatomic level, and something bizarre happens. An electron hitting a thin barrier doesn't always bounce back. Sometimes it simply appears on the other side, without ever passing through. This happens because quantum particles aren't solid objects. They're described by wave functions, mathematical shapes that spread out and fade at the edges but never quite reach zero. That tiny tail of probability is enough for a particle to leak through a barrier that should be impassable. For decades, physicists assumed this was strictly a microscopic phenomenon. The Berkeley team decided to test that assumption. They used superconducting circuits called Josephson junctions, cooled to temperatures colder than deep space, and looked for tunneling not of a single electron, but of billions of electrons behaving as one collective quantum object. The result was clear. At low temperatures, the escape rate became completely independent of temperature, something only quantum tunneling can explain. The result was clear. At low temperatures, the escape rate became completely independent of temperature, something only quantum tunneling can explain. For the first time, quantum behavior was proven at a human-relevant scale. This wasn't just curiosity. It laid the foundation for superconducting qubits, the building blocks of modern quantum computers. A discovery driven purely by the need to know, with no idea what it might unlock.